Good evening and welcome everybody. It's Obi-Wan Pez for Simplex Pachinko. We are doing some math communication tonight, looking at a historical, a paper on some math history, which is going to look at the binary exponentiation algorithm, and then we're going to look at we're going to see how much time we have left because the first paper is like 17 pages, so we'll see how that goes. And then waterproof editor, educational environment for proof assistance. So I hope you all are having a good evening or whatever else you got going on. And we're going to look into that paper. Just give me a second. My microphone volume was going off the chart before I got on here, but I wasn't doing anything, so that was a little confusing. Okay, anyway. Cool. On the history of the square and multiply algorithm by Nuh Aydin, Mohammed Azarian, Omid Kormali, and Gaia Mitimet. They are from the Department of Mathematics and Statistics at Kenyon College, Gambier, Ohio, and the Department of Mathematics, University of Evansville in Indiana. The square and multiply algorithm, also known as binary exponentiation or repeated squaring, is a technique for fast exponentiation commonly used in modern cryptography or computational number theory. Despite prominence, the historical origins of the algorithm are not known with certainty. This paper critically examines the origins and formalization of the algorithm through primary source analysis. We focus on Jamshid Al-Kashi's 15th century Miftah al-Hisab, where the algorithm is articulated explicitly as a general method and claimed by Al-Kashi as his own innovation. To contextualize this, we trace earlier instances of successive squaring in the works of... It would have helped if I had actually read this part beforehand. Al-Uqlidisi and Al-Biruni, who applied these techniques for specific calculations, but did not formalize them into a general procedure. The earliest known work on this method of computation is found in Pingala's prosodic studies in ancient India, roughly speaking 200 BCE. Even though it was not fully developed as a general technique, Pingala's work also seemed to contain the conceptual foundation of the algorithm, which is to employ the binary representation of a positive integer. By mapping this intellectual progression, the paper illustrates the historical background of an algorithm that is prominent in modern computation. All right, the square and multiply algorithm is commonly used computational technique in modern cryptography since it is a critical element for practical implementation of several crypto systems. These include many well-known public key crypto systems such as RSA, Diffie-Hellman, El-Gamal, and elliptic curve protocols for classical computers. Moreover, it plays a key role in many primality testing algorithms as well as quantum algorithms like Shor's to factor large integers and solve the discrete logarithm problem. It is also an important computational aspect of security analysis of various crypto systems, for example, in the context of side-channel attacks. Unfortunately, I don't think I have enough expertise in that. Due to its prominence in cryptography and number theory, section 2, the algorithm is discussed in almost every book on cryptography and many books on number theory. The importance of this topic motivates us to study its history, despite its prominence in modern mathematics. The historical origins of this algorithm are not fully known. The question of who first discovered or used this algorithm turns out to be more complicated than one might expect. Useful starting point is Don Knuth, one of the most authoritative references in computer sciences. It's in computer science who provides a brief historical sketch of the algorithm. He attributes an early appearance of the method to Pingala's Chandasastra, rule of metrics, before 400 AD. Then Knuth credits the Al-Uqaydisi of Damascus in 952 with giving a clear discussion of how to compute 2 to the n efficiently for arbitrary n. Knuth finally states that the great calculator Al-Kashi explicitly described the general right-to-left binary method for exponentiation in 1427. This sketch naturally raises the question of what exactly these earlier sources contain and how they relate to each other, which is the central motivation of this work. A number of other sources, ranging from educational websites, blog posts, to some academic publications, given here, also attribute the algorithm to Pingala, who lived around the 2nd century BCE. David Jones Show! How's it going? Good evening. If anyone is interested, we have the arXiv link right here. If you're on YouTube, hi YouTube, I have put it in the description and given a sort of reference. It's not exactly like it's not up to the standards of MLA or what have you, but APA. It's not up to the standards of APA, but nonetheless. Those of you who are not already on our YouTube channels, we have Obi-Wan Pez is our gaming channel, and at Nsimplex Pachinko 6542 is our mathy stuff channel. So if you have any interest in seeing some of the mathy stuff we do, go ahead and hop on over there, and we'll hope to see you in the next one. At some point in the near future, I am hoping to finally, hopefully, fix DaVinci Resolve. Oops, that was not the right button. Resolve. Yeah. DaVinci Resolve. And hopefully we'll be able to actually edit videos. Maybe. I'm not holding my breath, honestly. It has always had a major problem with Ubuntu, and that I know that is the distro that I use for Linux. Anyway, David Jones, how you doing tonight? Now that I'm off on that tangent. Okay. If true, this would mean that the algorithm has a much older history than is generally recognized. Knuth already states that this method is quite ancient, and he says it appeared in Pingala's Chandasastra. We analyzed the relevant evidence and primary sources to clarify the historical trajectory of the square and multiply algorithm. Since Al-Kashi claims to have invented the algorithm in the 15th century, we start by looking into his work. Al-Kashi presents the method quite explicitly in his comprehensive book, Miftah al-Hisab, which can be translated as Calculator's Key, or Key to Arithmetic. We prefer the latter translation, henceforth Miftah. He introduces it across 2 rules in the algebra treatise of Miftah, first in the context of computing the sum of a geometric series, then in a rule devoted entirely to computing large powers efficiently. Notably, Al-Kashi frames these contributions as rules he deduced himself, suggesting he viewed the method as his own contribution, which happens all the time, right? So people discover things. Oh, you're at work, so slow to respond. No worries at all. Um, given how slow I was to get to your message in the first place. Or rather, to ask you how your day was going. Um, yeah, so it happens all the time that people will discover concepts and ideas on their own in complete isolation to other people, or perhaps they have a slightly different formulation on the exact same thing that they once read a long time ago and have since forgotten, you know, what the thing was. They can't look it up again, especially back in the, what, 15th century. We're talking like 14th, 15th century. We're talking people who, had libraries all over the place, but like the system wasn't completely transparent. It might have been very hard to find a paper that you once read long ago. So, even if Al-Kashi did not actually invent this algorithm, A, perfectly possible that he did it completely independently, much like Newton and Leibniz with differential calculus. And it's also possible that he did just read something and then come up with it on his own much later. I guess not too much later because he only lived to 49. Ew. All right. Notably, Al-Kashi frames these contributions he deduced himself, suggesting he viewed the method as his own contribution. This makes Miftah al-Hasib one of the clearest and most explicit early treatments of this algorithm that we have found in the literature. More on Al-Kashi's broader mathematical contributions and the account of Miftah can be found in the following references: 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So, pretty good. Turns out that two earlier Islamic scholars, Al-Uqaydisi and Al-Biruni, both used techniques of successive squaring several centuries before Al-Kashi. Al-Uqaydisi, who was active in the 10th century, developed a systematic procedure for finding the amount in any cell of a doubling sequence using repeated squaring. Al-Biruni, in the next century, applied a similar chain of squarings to solve the classical chess problem, computing 2 to the 64th through 4 successive squaring steps. Neither of them did, however, present the method as a standalone general method the way Al-Kashi did. There was no explicitly named concept of algorithm in the 15th century or before, but Al-Kashi called it a rule. It appears like before Al-Kashi, the technique was embedded in specific problems rather than stated as a general rule. So that's also something that happened a lot. Obviously, they're stating it. But yeah, I can't think of any specific ones, but I've seen this. Yeah, it's not the exact same story, but it rhymes. Um, we've seen multiple other cases where something throughout history was just kind of done individually, one by one, to solve a specific problem, and then eventually somebody came around and formalized the whole thing, and, as they say, generalized, sitting as a general rule. So, Euler could be, no, not Euler, probably Euler. Euclid could have been seen as doing this in multiple places. So, the elements was not entirely his creation. Not only did he have co-contributors working with him at the time, but also he had taken a lot of earlier work and consolidated all of that into the elements altogether. Hey, Megalomorph. Trying to take Powers Mod N? I think so. I haven't read the whole paper yet, but... This paper investigates these historical threads. Section 2 discusses the importance and modern applications of this algorithm. Section 3 examines Al-Kashi's treatment of the algorithm in detail. Section 4 looks at earlier relevant works of Al-Uqaydisi and Al-Biruni, as well as Pingala's work on this topic. Section 5 offers concluding remarks on what available evidence suggests about the origins of the algorithm. Section 2. The algorithm, known variously as square and multiply, binary exponentiation, exponentiation by squaring, repeated squaring, and double and add in the setting of elliptic curves, is a broadly applied technique in computational number theory and modern cryptography. Core idea behind all these names is really the same. By writing the exponent in binary and performing a sequence of squarings and conditional multiplications, the number of operations needed to compute a to the n drops from O of n all the way down to O of log of n. Computationally, this reduction is highly significant. Since this is a number theoretical algorithm, the size of the input is log n rather than n. So, yeah, quite good. The naive algorithm computes a to the n by performing the sequence of computations. A squared is equal to a times a to the third is equal to a times a squared, etc., all the way to a to the n is equal to a times a to the n minus 1. Therefore, its complexity is O of n, which is exponential time because n equals 2 to the log of n, whereas the log base 2, ooh, all right. Oh, because we're working in binary, so therefore the default log should be the base we're in. Okay. I don't like it, but I guess. Whereas the square and multiply algorithm is linear in the size of the input, hence it is an efficient algorithm. To demonstrate the difference this makes in practice, we include the outputs of actual computations, helpful, to from two different computer algebra systems, Maple and Magma, using the naive algorithm versus the efficient algorithm. The following examples show that while modern computer algebra systems cannot handle the computation when the command to do the computation uses the naive method, they instantly compute the result when the efficient method is called. Right, so calculation of a to the e, in this case, 3,567 raised to the million, billion, 24,556,677,888,111. N equals 10 to the 9th plus 27. Right, so we get an overflow in Maple attempting to do 3567 raised to the 24-ish trillion power. Yep. Calculation of a to the e mod n in Maple using efficient immediately comes back. Right, submit to have evaluated by Magma. Here we have error. And again, here we have actual. sorry, this is just, yeah, argument is too large. And then when we do the efficient, total runtime 0.01 seconds. This one was 0.02 seconds to hit overflow. Here, 0.01 to hit the actual value. Knuth gives a thorough treatment of this algorithm in 23, and Schneier's Applied Cryptography, 35, describes it as a cornerstone of practical implementation of several public key crypto systems. The algorithm shows up in many important areas, some of which we summarize below. One of the most important uses of the algorithm is in computing modular exponentiation, h to the e mod n, which is the core arithmetic operation RSA crypto system and the Diffie-Hellman key exchange. Without this technique, RSA encryption and decryption with 2048-bit keys would simply not be feasible in practice. The algorithm is also needed in the Al-Gamal crypto system and digital signature algorithm, or DSA, both of which rely on computing large modular powers efficiently. Algorithm also plays a central role in primality testing. Both the Fermat primality test and Miller-Rabin primality test need to compute a to the n-1 mod n for large values of n. Without fast modular exponentiation, generating the large primes that RSA key generation requires would not be practical. It also appears as a key subroutine in the AKSX deterministic primality test. Modified version of the algorithm is used in elliptic curve cryptography. In the setting of elliptic curves, the group operation is point addition rather than multiplication, and a scalar multiple of a point instead of an exponent for a large integer needs to be computed. The analogous technique in this setting is called double and add. To compute the scalar multiple kp of a point p for a large positive integer k, one doubles and continually adds according to the binary expansion of k. This is the operation at the heart of elliptic curve Diffie-Hellman key exchange, elliptic curve digital signature algorithm, and related protocols standardized by NIST and the NSA. As Lee et al. Wrote, the double and add method is directly inspired by the repeated square and multiply algorithm, has been long considered a fundamental technique in this area. The algorithm also shows up in a perhaps unexpected place, namely quantum computing. Modular exponentiation via repeated squaring is the computational bottleneck in Shor's quantum polynomial time factoring algorithm, where it has to be implemented using a circuit of reversible gates. This means the algorithm matters not just for the cryptographic systems in use today, but also for the quantum algorithms that could threaten those systems in the future. Widespread use of the square and multiply algorithm has also made it an important target in security research. Koch's timing attack showed that the difference in execution time between squaring and multiplication steps can leak private key bits from RSA implementations. Interesting. That finding led a large body of work on constant time variance, including the Montgomery ladder algorithm, and on implementations that resist power analysis attacks. A to the 2k is equal to a squared to the k. Yep. A to the k, 2k plus 1 is equal to a times a to the 2 to the k. Yeah. Produce any power by repeatedly squaring and multiplying by a. Yeah. Ghiyath al-Din Jamshid Masud Al-Kashi, usually referred to as Al-Kashi and sometimes Al-Kashani, was one of the most renowned mathematicians and astronomers in Persian history, and one of the most fascinating medieval Muslim mathematicians. We'll very briefly introduce his significant works in mathematics and astronomy. All the lead up is going to be for that algorithm. Yeah. Oh, we're counting on it. One of the most notable mathematical achievements of Al-Kashi is Al-Risala al-Mukhitiyya, treatise on the circumference, which he completed in Arabic in 1424. This treatise he correctly estimated 2 pi to 9 sexagesimal digits, which is equivalent to 16 decimal places of accuracy. Second important mathematical achievement of Al-Kashi is Risala al-Watar wal-Jaib, treatise of the chord and sign, which he finalized between 1424-1427 in Arabic. Al-Kashi applied Ptolemy's theorem to an inscribed quadrilateral to obtain his famous cubic equation, and then invented an ingenious and quickly converging iteration algorithm to calculate sine of 1 degree to 16 correct decimal digits. Again, 9 sexagesimal places as a root of his cubic equation. Since we've been doing all of this stuff, or were they doing all of this stuff in sexagesimal explicitly because degrees were split up into 60 minutes and then 60 seconds due to the Babylonians? Oh, man. There's a good chance that's true. Yeah, presumably, yeah. Oh, man. Alright, used at the root of his cubic equation. It's remarkable that Al-Kashi used both geometry and algebra to approximate sine of 1 degree to any desired accuracy. Not only was this the most creative method of approximation, but it was one of the first known approximation methods in the history of mathematics and a substantial achievement in medieval algebra. The third and most well-known mathematical work of Al-Kashi written in Arabic is Miftah al-Hisab, calculator's key, key to arithmetic, henceforth Miftah. Contains some of Al-Kashi's original findings as well as improvements on earlier works. Written primarily as a textbook, Miftah was used for more than 5 centuries. Not only as a textbook, but also as an encyclopedia. Served many generations of students and professionals. It took Al-Kashi more than 7 years to bring Miftah to fruition. On 2nd of March 1427, Miftah has been recently translated to English in full. More on Al-Kashi's contributions and the content of Miftah can be found in the following. How recent are we talking? 2022. Yeah. Special cover book. Sent from Springer. 180 GBP, and it can be yours. I mean, I understand that people, especially the people who worked on it really hard, need to earn some money, but at the same time, yikes. Might be able to get it through ResearchGate though. Anyway, curiosity. 13. Bergren, Episodes in the Mathematics of Medieval Islam, 2nd edition, Springer. And then 3, 4, 5, 6. Yep, Volume 1, Volume 2, Volume 3. Okay. 19, 20, 22. Nice. Presumably there is also a copy that is all three of them put together. That was probably the 180 pounds one. Al-Kashi was also a prominent astronomer who served as the director of the Samarkand Observatory, which was the most advanced observatory of its time. Al-Kashi completed some of his best works at Ulugh Beg's Observatory and Madrasa in Samarkand, 1420 to 29, where he was recognized as the leading mathematician and astronomer. Some mathematical discoveries were in conjunction with his various works in astronomy. Best known are Sulam al-Sama, the Ladder of the Sky or Stairway of Heaven, completed in Arabic, 1st of March 1407. Muqtazar Dar Ilm-i Khayat, Compendium of Science and Astronomy, finished in Persian in 1410 to 1411. Risala Dar Shar'i Alat-i Rasad, treatise on the explanation of observational instruments, concluded in Persian in January 1416. Nuskha al-Hadaik, the Garden Excursion, finalized in Arabic February 10th, 1416. And Zish-i Kakhani, the Kakhani astronomical tables, completed in Persian 1413 to 14. This is a revised version of Nasir al-Din al-Tusi's. Yep. Al-Tusi was also a famous mathematician and astronomer, so you can check out his stuff at some point, I'm sure. The method of square and multiply appears in Miftah, even though it is not specifically named method. Hey, Famished, how's it going? First mentioned in the context of computing the sum of an sum of a geometric series. 5th treatise of Miftah is devoted to algebra, which is about a third of the entire book, the other two being on arithmetic and geometry. The 3rd chapter of Treatise 5 is titled On Some Computational Rules That Are Crucial to Find Unknowns and contains 50 rules. In Rule 9, Al-Kashi describes the square and multiply algorithm for the first time in Miftah. However, the main goal of this rule is to give a formula for the sum of a geometric series. Later, he gives Rule 16, which is specifically devoted to the algorithm by itself. Here's the full statement of Rule 9. The 9th rule. Doing some Python, doing some maths. Nice. On the sum of numbers resulting from doubling one or another number. This is also from what we would deduced. The way to do this is that if the last number of this sequence is known, we subtract 1 from its double. The result is the sum of those numbers. If the last number is unknown, we look at how many times we duplicated. That is the rank of a multiple. That multiple is obtained from a first ratio of 2. The way to obtain this, to obtain the multiple, is to see if the rank can be halved over and over until it becomes 1. We then look to see how many times it is halved until we get 1, or we know the power of 2 with its rank. We square 2 again and again as many times to get that number, as many as that rank. That is, we multiply 2 by itself, then the product by itself, and the second product by itself, and so on, as many times as to get that number. To obtain the last number, we double it, previous number, and always subtract 1 from it. The result is the sum of those numbers. We initially add 1 to the numbers that are multiples, and if the sum of some multiples can be halved until it becomes 1, then we use it to do some same computations as earlier. The result is the sum of the numbers with 1 added to it. Goodness. As was custom at the time, Al-Kashi explains everything in prose. Algebraic symbolism was not yet introduced. True. Al-Khwarizmi wrote his algebraic book in the early 9th century. It was the first time in history that algebra was specifically named as a technical mathematical operation. The English word algebra is also a transliteration of the Arabic word al-jabr that appears in the title of his book, which is also very large. The actual name of the book is like on the method of I can't remember exactly what it is, but it's like on the method of writing equations or something. Not like writing, making right. Might as well. Concise book of calculation by restoration and balancing. Yep, that was it. Restoration and balancing was really the thing that I was remembering, but not really. Okay. 6 centuries later, when Miftah was written, there were still no symbols in algebra. Al-Kashi explains that this rule is about finding the sum of geometric series with common ratio 2, whose initial term is either 1 or some other number. In subsequent explanations, he seems to be working with the case that the first term is 1. Therefore, he considers the geometric series sum as I goes from 1 to n of 2 to the I minus 1. If we know the sum of this series, then the case when the first term is some other number a is easy to handle because the sum as I goes from 1 to n of a times 2 to the I minus 1 is equal to a times the sum, the above sum. Al-Kashi implies that this formula is among the things that he either discovered or invented. His claim needs to be examined by researchers. Al-Kashi says that if the last term of the sequence is known, then the sum equals twice the last term minus 1. That is, he gives the formula summation of powers of 2, 1 plus 2 plus 2 squared plus 2 to the third, etc., plus 2 to the n is equal to 2 to the n plus 1 minus 1, which is the correct formula. He then considers the case where the last term in the series is not known. In this case, he finds the exponent, say n, of the last term of the series, 2 to the n, from the number of terms. To compute this numerical value of the last term, he divides n by 2 consecutively until he does obtain 1, if possible. First, he assumes that n can be divided by 2 consecutively until 1 is obtained, say m steps. Then he computes 2 to the n as being the m successive squares, 2 to the second, to the second, to the second, etc. After this rule, Al-Kashi gives a sequence of examples. In the first, he computes the sum 2 to the I as the sum of 2 to the I as I goes from 1 to 8. As a first step, he computes 2 to the 8th via the square and multiply method, i.e. computing 2 to the second, to the second, to the second, which requires 3 squaring operations as opposed to the direct method of computing 2 times 2, 2 times 4, 2 times 8, 2 times 16, 2 times 32, 2 times 64, 2 times 128, which equals 256, which requires 7 multiplications. He doubles that last number, subtracts 1 from it to get 2 times 256 minus 1, which is 511. He subtracts 1 again to find 510, which is the sum of 2 to the I as I goes from 1 to 8 rather than 0 to 8 as it was before. Next, he considers the well-known chessboard problem, which amounts to computing 2 to the 63rd. The way Al-Kashi solves this problem is to first compute 2 to the 64th by a square and multiply. That is computing 2 squared, which is 4, 4 squared, which is 16, 16 squared is 256, 256 squared is 65,536. That squared is roughly 4.3 billion squared, which then is another number. All right, millions, billions, trillions, quadrillions, like 18 quintillion, and then square it, because 64 can be repeatedly halved until 1 is obtained, i.e. it is a power of 2. He then halves the last number to obtain 2 to the 63rd, which he finds to be that given number here. Billions, billions, wow. Million, billion, trillion, quadrillion, 9.2 quintillion. After this example, Al-Kashi makes the following comment. As for when the number of doubles cannot be halved over and over, to get 1, we subtract it from the largest number that can be halved until it gets 1. Then the same from the remainder, and so on and so forth, until nothing is left, or there is 1 left. So the number is decomposed into these numbers. He gives a quick example. If the number is 10, we can decompose it into 2 parts, 8 and 2, each of which are powers of 2, so they can be halved until 1. Next, considers an example where the number is broken into 3 parts, such that each part is a power of 2, i.e. 64, 32, and 4 from 100. Though Al-Kashi does not explicitly name 100, he still does this stuff. He gives a detailed explanation of how to compute 2 to the 100th power, then obtains the summation as I goes from 0 to 100 of 2 to the I. In the next example, he explains how to compute the sum as I goes from 0 to 11 of 2 to the I, in which he starts breaking up 11 as 8 plus 2 plus 1. Next, Al-Kashi makes the point that if the first value in the sequence is a number other than 1, and if we double each term at every step, we can find the result using the following formula. In rules 10 through 15, he gives the formulas below, all in words without proofs. He stated that rules 7, 9, 15, 16 were his own discoveries. Here are the formulas in modern notation that Al-Kashi stated in words in those rules. Alright, Rule 10 was the summation of I times I plus 1 from 1 to the n. Rule 11, the summation of I times I plus 1 times I plus 2 from 1 to n. Rule 12 is the sum of squares from 1 to n. Rule 13 is the sum of cubes from 1 to n, and Rule 14 is the sum of fourth powers from 1 to n. Remark, it is intriguing that about 4 centuries prior to Al-Kashi, Ibn al-Haytham, known as Al-Khazin, discussed the summation of all fourth powers from 1 to n in his treatise on determination of sums and powers of numbers. Rule 15, the general, that's fun, the general rule of a to the I summed as I goes from 1 to n, where a is any number except 1. For a being p over q less than 1, Al-Kashi presented the following formula, This is the sum of p over q raised to the I as I goes from 1 to n. It's going to be this stuff. Then comes the 16th rule, which is entirely devoted to the square and multiply method. So here's the full statement. You get a large power of a number without finding the consecutive powers between them. Okay, it's not the whole page. That's what I was worried about. This is also from what we deduced. We take the power and check if it can be halved until 1. If it is, we find the number of times it needs to be halved to get 1. Then we square the first power as many times until we get the final power, which is the wanted value. Then he gives 2 examples. In the first, he computes 5 to the 8th. Here, 8 is a power of 2, and 1 is obtained by halving 8 3 times. Therefore, he obtains the result by 3 squarings. So 5 squared is 25, 25 squared is 625, and 625 squared is 390,625. He then explains how to apply the method if the exponent is not a power of 2. He writes, if the power cannot be halved until 1, we subtract it from the largest number possible that can be halved by 1. Then do the same with the remainder, and so on until either nothing's left or 1 is left. We get numbers whose sum equals the wanted power, and each of them can be halved until 1, or one of them is 1 itself, and the others can be halved until 1. Right, so summation of even numbers is going to get you an even number left over at the end, or 1. We just keep subtracting those even numbers. Well, I guess it's 0 or 1, right? This is where we get the binary representation and the binary this binary idea. We'll talk about that in the next paragraph. Looks like find the count of the halvings required to each number to get to 1. Write it next to the respective number. Then we write 0 next to the 1. Count these. We call these counts the number of times. Then we square the first power again and again as many times as the largest of the numbers of times. We write the last square next to the respective number. Similarly, if we write next to each number the last square, which results from squaring the first power, a number of times corresponding to that number. We put the first power next to the 0. Then we multiply these powers in the column by the others. The result is the last power that is wanted. In this case, Al-Kashi explains the technique to compute a to the n, where n is not a power of 2, as follows. Breaks up n as n equals n1 plus n2 plus n3 plus etc. to nk, where the numbers n1 through nk are powers of 2. He obtains the binary base 2 representation of n, then computes b sub I equals a to the n sub I for each I using the 16th rule. He then multiplies all b sub i's to obtain a sub n. Next, he gives an example to illustrate how to apply this technique to compute 4 to the 14th. First step, to write 14 is equal to 8 plus 4 plus 2. Then computes 4 to the 8th, 4 to the 4th, 4 squared, and finally multiplies all those results together. I guess. Earlier works. As noted prior, 2 Islamic scholars predate Al-Kashi in their use of successive squaring. Al-Kashi in the 10th century and Al-Biruni in the 11th century both employed repeated squaring to compute large powers of 2 efficiently. Several centuries before Al-Kashi articulated the method as a general rule. However, neither of them presented the technique as a standalone general method. Rather, in both cases, the method was embedded within specific computational problems. In this section, we examine what each of these scholars did, followed by a discussion of Pingala's earlier work. Al-Biruni In the chronology of the ancient nations, Al-Biruni addresses the same classical chess problem requiring the computation of 2 to the 64th minus 1. He presents two fundamental rules. The first states the square of the number of a check x of the 64 checks of the chessboard is equal to the number of that check whose distance from check x is equal to the distance of check x to the first check. As an example, Al-Biruni takes the square of the number of the fifth check, i.e. 16 squared, which is 256, which is the number belonging to the ninth check. Since the distance from the ninth check to the fifth check is equal to the distance between the fifth check from the first, which is the number belonging to the ninth check, since the distance of the ninth check from the fifth check equals the distance from the fifth check from the first. Second rule states the number of a check x minus 1 is equal to the total sum of the numbers of all preceding checks. As an example, the number of the sixth check is 32, and 32 minus 1 is 31, so therefore that equals 1 plus 2 plus 4 plus 8 plus 16. Using the first rule, Al-Biruni computes 2 to the 64th through a chain of successive squarings, expresses this as 16 squared, 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 which is 16 to the 16th, which is 2 to the 64th. Tracing the following chain of checks and their values, I have here the fifth check is the starting point, which is 2 to the 4th. Ninth check is the square of the fifth, which is 256. 17th is the square of the ninth, which is 65,536. 33rd check is the square of the 17th, which is going to get us 4,294,967,296. And the 65th check, therefore, is the square of the 33rd, and that is going to get us quadrillion, 18 quintillion, 446 quadrillion, 744 trillion, 73 billion, 709,551,616. He then subtracts 1 to obtain the total sum of all checks of the chessboard, arriving at same number, 18.4 quintillion, but then ending with a 615 rather than 616. Al-Uqlidisi, in the Arithmetic of Al-Uqlidisi, Book 4, Chapter 32, titled On Doubling 1 64 Times. Al-Uqlidisi addresses the problem of computing the number of any cell by a doubling sequence, as well as the total of all cells up to a given one. Begins by establishing a standard of 10 cells: 1, 2, 4, 8, 16, 32, 64, 128, 256, and 512, to which he reduces all subsequent computations. He observes that multiplying the number in any cell by its like, i.e. squaring it, gives the number in twice the cell number minus 1. For example, the number on the fifth cell is 16. If you square 16, you get 256, which is the number on the ninth cell. The total of all cells up to that last one, 128, is going to then be 256 minus 1, which is 255. Al-Uqlidisi's method for finding a number in an odd-numbered cell proceeds by adding 1 to the cell number, then halving it, then using a 10-cell standard. For the 17th cell, he states We add 1 to 17, take half of that, finding 9. We then multiply what is in the 9th cell by its like, 256 times itself is 65,536, which is the amount in the 17th cell. For the 51st cell, Al-Kashi proceeds as follows. Increase 51 by 1, take half is 26, take half, which is 13. Add 1 and take half is 7. Add 1 and take half is 4, in which we find the number 8. Then computes upward through successive squarings. So 8 squared is 64, that squared is 4,096, that squared is 16,777,216. Because we multiply by 2 because we're just going up a cell to the 26th cell, and then we're squaring that number, 33,554,432, squaring that to end up getting us this million, billion, 1 quadrillion, 125 trillion, 899 million, no, that's billion, 906,842,624. That is, after reaching the 25th cell, he doubles the amount to reach the 26th, then squares it to reach the 51st cell, because that's going to be double 26 minus 1. For even-numbered cells, Al-Kashi states that 1 halves the cell number and adds 1. Sorry, that 1, i.e. a person. 1 halves the cell number and adds 1, then proceeds as in the odd case. Consider the 14th cell. Take half of 14, which is 7, then add 1, take half of that, which leads to the 4th cell, in which we find the number 8. He then computes 8 squared is 64, 64 squared is 4,096, double that is 8,192, which is going to be our 14th cell. After reaching the 13th cell by 2 successive squarings, he doubles the amount to obtain the value in the 14th cell itself. Okay. We shall return in about 3 minutes. So I'll leave this here. We'll take a 3-minute ad break. Everybody get up, stretch, take your meds if you need to, do all that good stuff, and we shall return. See you soon. Thank you so much for coming. left that on. Whoops. That's all good. Hope you all are having a good evening. We're going to continue on probably the rest of this paper. How things go. Thanks for sticking around. Okay. So, Pingala, ancient Indian scholar who is credited with writing Chanda Sutra, the treatise on Sanskrit prosody concerned with the systematic study of metrical patterns in poetry. A number of sources ranging from educational websites and blog posts to some academic publications attribute the square and multiply algorithm to Pingala, sometimes calling it the earliest known instance of binary exponentiation. Smith states that the binary method appeared before 400 AD in Pingala's Chanda Sutra. Therefore, Pingala deserves a careful examination in any discussion of the history of the square and multiply algorithm. One thing we notice is that many of the sources do not directly engage with Pingala's original text, and apparently appear to rely on each other rather than on independent primary source analysis. Yay! I do have to admit that is where a lot of my stories end up coming from. Is, you know, somebody said this at one point, whether it be one of the mathematical non-fiction authors that we read, or whether it be or whether it be our professors who told us stories when we were in undergrad. And we just keep passing them down. However it works, or seems to work. For instance, blog posts and educational websites given here make statements that Pingala invented binary exponentiation without providing direct textual evidence from Chanda Sutra itself. The academic paper by Sahu similarly attributes algorithmic thinking to Pingala but draws on secondary literature rather than primary sources. One of the scholarly treatments of Pingala's original work that we found is the paper by Shah, which systematically traces Pingala's algorithms through Indian mathematical literature over more than a millennium. Shah does describe a divide and conquer recursive algorithm in the Chanda Sutra for computing powers of 2, specifically the algorithm for calculating the total number of possible metrical forms of a given length. In Pingala's scheme, if the number of syllables n can be halved, the result is obtained by squaring. And if not, 1 subtracts 1, then doubles. This is expressed in 4 cryptic sutras and is used to compute s sub n equals 2 to the n, the total count of all forms of n-syllable meter. The algorithm is recursive, and it does rest on the same underlying mathematical principle as square and multiply technique. In this sense, Pingala does use a method that is mathematically equivalent to binary exponentiation. It is interesting to note that Pingala's use of this technique is entirely embedded within the specific problem of counting metrical patterns. In Sanskrit poetry, it is not presented as a general computational method for computing arbitrary powers of a given number. Joseph's The Crest of the Peacock discusses Chanda Sutras exclusively in the context of combinatorics and Pascal's triangle, with no mention of a general exponentiation algorithm, because in that particular thing they're talking about, I believe, the choice to use either a long or a short syllable, or I think it's syllables, long or a short item at any individual moment in the poem. So it ends up becoming an n choose k problem, which is why Pascal's triangle gets a mention here. Well-known expert in the history of Indian mathematics is Kim Plofker. Plofker's chapter in 28 and book 29 describe Pingala's work related to binary exponentiation in the context of prosody and combinatorics. In the section titled Mathematical Ideas in Other Disciplines, in her book, Plofker describes Pingala's method of using a succession of squaring and doubling operations to calculate 2 to the n. She, rather than Pingala himself, illustrates the algorithm via the example of computing 2 to the 7th. In section 5.3 of 29, her book, Plofker states that a later Indian scholar presents a more general version of Pingala's technique to compute r to the n. Plofker states that this scholar was a medieval 9th century namesake of Mahavira, the founder of Jainism, 6th century BCE. The number theoretical algorithm known as square multiply binary exponentiation or repeated squaring is an important algorithm in modern computational number theory and cryptography that enables fast exponentiation of numbers of the form a to the m mod n for large integers m and n. Tracing historical origins of this algorithm, we find an explicit description of the algorithm as a rule in Al-Kashi's 15th century book, Mitfach al-Hisab. Although Al-Kashi seems to claim that he discovered the algorithm himself, scholars well before Al-Kashi wrote about it. For example, two Islamic scholars, Al-Uqaydisi and Al-Biruni, who predate Al-Kashi by several centuries, employed successive squaring to compute large powers of 2 efficiently. Al-Uqaydisi's treatment is presented as a general procedure, while Al-Biruni's treatment is presented specifically in the context of the chess problem, tracing a fixed chain of 4 squarings from 5th to 64th check. Going further in history than Islamic scholars, there is evidence that the ancient Indian scholar Pingala had the main idea of the square multiply algorithm, which is to use the binary representation of the exponent, even though it was in the context of counting metrical patterns. Using the binary representation of the exponent is the essence of the algorithm that makes it efficient compared to the naive algorithm, which has exponential running time. There is sufficient evidence to conclude that Pingala had the basic idea and explained it in an elementary way in the context of counting metrical patterns in the 3rd or 2nd century BCE. Though it was not initially stated as a general mathematical procedure, on the basis of available evidence, Pingala may be viewed as the first person who used a procedure that we now call square multiply algorithm. Ooh. Cool. All right, bit shorter. Waterproof editor, an educational environment for proof assistance and programming languages, by Pim Ott, Mathematical Institute, Utrecht University, the Netherlands, Dick Arends, Radboud University, Nijmegen, Raul Sanchez Flores, Department of Mathematics and Computer Science, Eindhoven University of Technology, along with Pieter Wills and Jim Porteghis of the same. Waterproof editor. And there is the arXiv link for that one. Waterproof Editor provides an educational environment specifically targeted to teaching with proof assistance or programming languages. It arose from Waterproof, educational software targeted at helping students acquire the skill of giving mathematical proofs. Its original features, such as enabling rich formatting and providing clear input areas, are now abstracted away in an NPM package and can be used in different educational contexts. We invite interested parties to use this component in their educational software and to offer to assist with this. We propose to demonstrate Waterproof Editor, an environment that was originally designed to work with proof assistance in education. Waterproof Editor was initially a tightly interwoven part of Waterproof 7, an educational tool aimed at helping students learn to write mathematical proofs. Waterproof was built on top of the Proof Assistant ROC and leveraged this to provide students with immediate feedback. In Waterproof, students can write their proofs in designated input areas. These input areas are colored on the basis of evaluation of proofs. Accidental edits outside of these input areas are prevented. Diagnostic messages are clearly presented underneath input blocks, and Markdown is rendered to provide documents with a structured look. See Figure 1. From a desire to also have such an environment available for working with other proof assistants, in particular Lean, we split off large parts of this functionality into Waterproof Editor project. Given above, screenshot of Waterproof with an input area designated by the red bar. The bar is red as the proof is not yet complete. In the following exercise, you need to show that 4 is equal to the supremum of bracket 0 to 4 soft bracket. Alright, with abstracting a lot of features in Waterproof to Waterproof Editor, the environment suddenly also becomes useful for many other purposes. For instance, for working with programming languages. Conceptually, the only requirement is an evaluation function on the content of input areas. In this demo, we will present several use cases in which these evaluation functions determine whether a proof is correct or whether JavaScript code passes a suite of tests. Furthermore, since Waterproof Editor is distributed as an NPM package, it helped us realize a long-standing wish of creating a browser-only version of Waterproof, in which teachers or students can try out or even work with Waterproof without any installation by just following a link. It is certainly helpful. For instance, we have the Octave version that is just entirely online. It's very nice to be able to work with that stuff and not have to download the software unless you just you want to work with it. And having it local means that A, you can work with it offline, and B, it's pretty significantly faster since you don't have to worry about network requests. We see it as a large advantage that Waterproof Editor allows teachers to provide assignments to students in which the solutions can be put in the same document as the exercise statements. In the demo, we will show several use cases, including a version of Waterproof for Lean, programming exercises in JavaScript, and the browser version of Waterproof. We extend an open invitation for people to imagine and implement new applications for which we would gladly provide the help. Jump over to Discrete, yeah, discrete. That's what I want. I'm gonna pop that on. Thanks, Famish. I added Lilith here to a playlist called Feminist Rage Core. I'm here for it. Okay. Right. Section 1.1 related work. With the respect of mixed prose code documents, several projects are closely related. This is also known as pseudocode. A lot of times people will just like write what they want to have happen in a particular algorithm and then not worry specifically about what language they're using, and they're more worried about the type of English language that they're using rather than the type of computer language that they're using. It's a good way to kind of informalize your coding process, to just kind of get a sense of what you want to have happen, and then you can also decide afterward what kind of computer language you're going to need. Okay. Electron combines the mixed document format with full elaboration for either lean or ROC code, yielding standalone documents with elaborated proof states. JSCOC provides an interactive standalone browser environment and pioneered the web worker infrastructure we reuse for our use case of waterproof in the browser. Jupyter notebooks share conceptual and visual similarities, but generally allows out-of-order execution, which is unsuitable for our case. Prose Mirror and Code Mirror are the major components used to realize waterproof editor. Zeproche provides a controlled natural language environment built on top of a custom automated theorem prover, while verbose lean uses lean, naturally. For the use case waterproof with lean, we have combined verbose lean with Verso, a documentation system for lean that allows for documents to be written alongside the formalization. Waterproof has been developed at Eindhoven University of Technology and used in Analysis 1 course since 2019. In 2025, Waterproof has been piloted in the Introductory Proof course at Utrecht University. For a more complete review, see 6. Waterproof helps students, oh nice, it is clickable. Waterproof helps students learn the skill of writing mathematical proofs. Waterproof presents the feedback from a proof assistant, ROC or lean, and uses a layer of controlled natural language, Coq waterproof or verbose lean, to ease the transfer of skills obtained to writing paper proofs. Previous work has evaluated the use of waterproof in education through the lens of service design 8, as well as the effect on the structure of proofs that students deliver 9. The latter showed that the proof structure used by waterproof users differed in 3 ways from the structures used by non-waterproof users. Waterproof users did introduce variables more often, and they announced the goal to be proven more frequently. But at the same time, they were more likely to forget to check domain conditions and quantifiers. Nice. This third finding has been traced to a specific aspect of waterproof and has since been improved. Also nice. Slightly less ironic nice. All features of Waterproof Editor have been designed for the purpose of mathematics education. Markdown rendering provides students with nicely formatted exercise sheets, increasing readability. Collapsible areas have a dual use for static hints, which students can reveal on demand. Technical details which might be unfolded by a teacher for debugging purposes. Input areas prevent the students from accidentally editing the rest of the document, which includes exercise statements. Feedback and messages are displayed in the document to decrease the amount of different areas students need to pay attention to. Visual editing of the document allows teachers to interactively check the exercise sheets as if they were a student, and keeping the option of plain text editing ensures that teachers who are power users of the underlying proof assistant can edit exercise sheets with their usual workflow. Oh yes, power users. Go man. Markdown rendering. To give the documents an attractive and structured look, we make use of markdown rendering. Screenshot figure 1 shows a boldface header accompanying text and a rendered LaTeX formula. It's also possible to embed pictures and videos. I believe that this rendering has many advantages instead of presenting text-based proof documents. Certainly the resulting rendered document has many similarities with Jupyter notebooks, while the underlying document is very difficult. Waterproof Editor allows for collapsing certain areas of the documents that they are not visible to the user by default. This is, for instance, useful in providing an optional hint to students that only unfolds when they actively click it, or when one would not want to distract the user with various technical details, again, unless they need it or want to look at it. In the document figure 1, it is used to hide all the statements that import the libraries and set up automation for the exercise sheet to work. Set up the automation for the exercise sheet to work is something the students definitely don't need to pay attention to. Now, it is helpful, I think, for students to see stuff like that at least once, to kind of look at it and be like, oh, this is something that's necessary. Explain it to them if they ever ask. Even if they don't, maybe just explain it to them. Students write their solutions in designated input areas. In figure 1, the red bar next to the input area indicates the proof is not yet complete. In particular, this example, the bar would also color red if the solution until that point would contain an error. If the input block would only contain a warning, the bar would be colored orange. If the evaluation is not yet complete, the bar would be blue. The exact meaning of the colors in Waterproof Editor is customizable. One only needs an evaluation function. We note that this evaluation function can be reused in server-side automatic grading of exercises. The main advantage of specifying areas in which the students can edit is that we prevent them from accidentally changing anything in the exercise sheet outside the input areas. Our experience in another large course at Eindhoven, relying on Jupyter Notebooks for Python programming, was that if one does not prevent such accidental edits, they will invariably happen, rendering the exercise sheets useless, either for the students themselves or later when they have to submit them. Yeah. We rely on a feature of Code Mirror that allows for putting diagnostic messages directly underneath code blocks. We use this feature to communicate error messages and warnings, but also to give students suggestions on what to do next, including buttons that allow students to carry through fixes or suggestions with a single click. See Figure 2 below. Right, expand all. Alternative characterization supremum. Oh. Yeah, replace. That looks like paste. Expand all. Code block with suggestions on what to do next. Pressing replace button would replace the line with expand A11 by the suggested alternative characterization. Screenshot of editor, verbose lean exercise. An important core design principle is that waterproof documents should be editable for students and teachers in both waterproof and plain text format using the standard tooling. Standard waterproof documents are MV files, which are effectively markdown files in which code blocks contain rook code. Expert teachers can then easily manipulate an exercise sheet in plain text mode, while if teachers want to immediately have that feeling on what an exercise sheet would look like if they render it, they can edit in waterproof. As a first use case for waterproof editor, we present support for verbose lean in waterproof. It provides the same editing functionality as the original rock-based exercise sheets. Of course, to make this work, also changes the waterproof VS code extension were necessary, but splitting of waterproof editor made this significantly easier. Not all test cases passed. Hello world, yay. Large part of this extra work is performed as a software engineering project at Eindhoven University. Our waterproof goal window was replaced using Lean 4 InfoView package, and some ROC LSP client functionality could be abstracted and reused. We implemented a custom Verso genre to ensure the plain files can be edited with these standard tools. Verso provides full support of Markdown-like syntax with the exception of preamble that needs special treatment when parsing. Use of waterproof editor is not limited to proof assistance. As validation of the functionality, we implemented a proof of concept using the editor for a different educational context, namely for teaching algorithms and programming with JavaScript. In this case, the colors next to the input areas get different meanings. Input area turns green if all test cases have passed, turns red or if one or more test cases fail. If that happens, the diagnostic error message underneath informs the student. Bar next to the input block turns yellow if the execution exceeded a predetermined time limit. In that case, execution timed out warning appears. Another advantage of waterproof editor is that it's easy to use it in a different environment, such as in a browser environment. For years, it has been an objective that the waterproof team make a version of waterproof that runs fully within the browser. We got much closer to this objective with the release of a WASM web worker for ROC LSP. Relying on this web worker, in the summer of 25, we released a version of waterproof that was able to run on vscode.dev. Note that no external server was necessary for this to run, and students did not need to install anything. The easiest way to work with this requires students to have a GitHub account. Working with a local folder is also possible, and it only takes a few lines of instructions to get started with waterproof in this way. By building on Waterproof Editor, we could build a version of Waterproof that runs fully within the browser, does not rely on web version of Visual Studio Code. This significantly lowers the barrier for students to get started, as well as for prospective educators who would want to test Waterproof. They have access to several exercise repositories to immediately start working with Waterproof code. In order to extend Waterproof with another language, all that's needed is to provide a language configuration, as well as a configuration for highlighting, possibly adapting one of the existing parsers to parse the exact on-disk format at the same time the document is first opened. For proof assistants, which generally have some amount of non-standard LSP functionality, some glue code is also required. Embedding Waterproof Editor in a similar way was the standalone version in the browser. Requires providing a configuration which contains a set of callbacks that allow the editor to communicate with the application. Either of these options are likely doable by student projects. Implementation of presented use cases required finding the rough edges for integration and allows future projects to integrate only by implementing specific details. Tooling that already supports a literate markdown-like format is likely very easy to integrate by reusing even more of the available infrastructure. We believe that the breadth of the presented use cases shows wide applicability of Waterproof Editor as a component in teaching tools. We hope that we can demo the tool at Teal and provide and excite some people to try to use Waterproof Editor for their own application. Could be interesting. Okay, well, I have it on GitHub. That would allow people to download it, although they said they wanted to have it available for not, having it just online. I'm not sure exactly how it's going to work, but fine. Okay. Maybe we can do that one next time. Righto. I think we're probably going to call it here. And we're going to come back tomorrow night and do some blueprints. Get back onto that. I left it for a few weeks there. Woo! That means we will head over to somebody. Solu is currently doing food and drink, making some cold noodle dishes. Ice cold nudes. Oh yeah. Paleontologizing. Dr. Danny Enduza is currently digging up a ceratopsian in Wyoming. They actually had a cast around the skull like 2 days ago. So we gotta see what they're up to. So they found one already, and it's pretty great. So I don't know if we're going to be able to see really much that's going on at the moment, but it's cool stuff. So come and join me, and we'll do some go ahead and copy that on over, and we'll that's weird. Okay, whatever. There we go. Copy that on over, and we'll throw it into Danny's chat. Thank you so much, everybody, for coming. My name's Obi-Wan Pez. This is N Simplex Pachinko, and